Welcome. Take a moment to settle into a comfortable position, somewhere you can rest quietly without being disturbed. Allow your body to soften and your breathing to find its own natural, steady rhythm. There is nowhere else you need to go and nothing else you need to do right now. This time is simply for listening, for drifting gently through ideas at an unhurried pace. Together, we are going to explore one of the most intriguing and mysterious questions human beings have ever asked, and we will do it slowly and calmly, letting each thought unfold with ease, giving your mind plenty of space to wander and rest at the same time. The question before us is both simple and deeply profound. Could the universe be a simulation? Could everything you have ever seen, felt, or experienced be part of something like an immense and intricate program? It may sound like a very modern idea, connected to computers and digital technology, yet in many ways this question has been with us for thousands of years. Across cultures and centuries, people have wondered whether reality is truly as solid and straightforward as it appears. Long ago, philosophers asked whether life itself might be a kind of dream. The Chinese philosopher Zhuangzi shared a story about dreaming he was a butterfly. When he awoke, he found himself unsure whether he was a man who had dreamed of being a butterfly or a butterfly now dreaming he was a man. This gentle and puzzling story captures a deep uncertainty about the nature of reality. When Zhuangzi woke, he experienced something familiar to all of us, a shift from one state of awareness into another. It raises a quiet question: which state is more real? We usually assume that waking life is solid and true, while dreams are fleeting illusions, but Zhuangzi invites us to soften that assumption. Perhaps both states are real in their own way, or perhaps both are appearances arising from something deeper and more fundamental than either one alone. In Hindu and Buddhist traditions, there's a long exploration of the idea of Maya, often described as the illusion or appearance of the physical world. According to these teachings, what we perceive as solid objects and separate things may not be the ultimate layer of reality. Instead, the world of forms can be understood as a kind of cosmic display, a flowing dance of appearances that gently conceals a deeper unity beneath. Spiritual practice, in this view, is a way of seeing through the surface, of recognizing that the many shapes and forms of the world are expressions of a single underlying wholeness. This is not exactly the same as saying the universe is a computer simulation, yet there are meaningful parallels. Both perspectives suggest that what we see on the surface may not reveal the deepest truth about existence. Another ancient image comes from the Greek philosopher Plato, who described a group of prisoners living in a cave. These prisoners could only see shadows cast on a wall and believe those shadows were the whole of reality. Imagine spending your entire life facing a single wall, unable to turn your head. Behind you burns a fire, and between you and the fire, people carry objects that cast moving shadows in front of you. Having never seen the objects themselves, you would naturally believe the shadows were real things. You would not suspect they were only projections, hints of a richer world you could not yet see. Plato suggested that our own experience of reality might be similar. What we take to be the real world could be like shadows of deeper forms, patterns, or principles that exist beyond our direct perception. His philosophy focused on abstract truths rather than digital systems. Yet the structure of his idea feels surprisingly close to the modern simulation concept. In both cases, our everyday reality might be a kind of representation, something that points beyond itself to a more fundamental layer we cannot easily access. These timeless reflections on the nature of reality find a new voice in our present age. Today we create virtual environments, digital landscapes filled with light, movement, and detail. We design physical rules inside these worlds, simulations of gravity, motion, and interaction. As our technology grows more advanced, these artificial realities become increasingly convincing. Characters move in believable ways, environments respond to touch, and entire worlds unfold inside circuits and code. As this happens, the ancient questions return with fresh energy. If we can build small simulated worlds, might it be possible that our own vast universe is part of something similar, though far more complex and sophisticated than anything we can currently imagine? This modern version of the idea is often called the simulation hypothesis. It asks us to consider whether consciousness itself could arise within a sufficiently advanced simulated environment. It suggests that the laws of physics we discover and measure might not be ultimate truths, but instead the consistent rules of an underlying system. In this view, the immense cosmos, with its galaxies, stars, and living beings, could be grounded in processes that resemble computation at a level far beyond our present understanding. This is not a question we can answer with certainty, and it may remain open for a very long time. Yet exploring it leads us gently into some of the most beautiful and mysterious discoveries of modern science. We find ourselves thinking about cosmology, about the origins and structure of the universe, about the nature of information, and about consciousness itself. There is no need to hurry toward conclusions. Each idea can be approached with patience, allowed to settle like ripples fading on still water. There is a quiet peace in contemplating such vast possibilities, in letting the mind stretch beyond everyday worries into a wider and more spacious perspective. As we continue, we will look at what modern physics suggests about the structure of reality, what theories of information and computation might reveal, and what scientists and thinkers have proposed about the deeper layers of existence. Some of these ideas are strongly supported, others are more speculative and imaginative, yet we can meet them all with the same gentle curiosity. Whether the universe ultimately turns out to be a simulation or something else entirely, the act of exploring the question opens wide and fascinating landscapes of thought. So allow yourself to settle even more deeply. Let your mind remain open, curious, and calm at the same time. We are beginning a quiet journey into the nature of reality itself, moving in a way that soothes the nervous system and invites reflection rather than urgency. The universe, whether simulated or fundamental, is endlessly rich and full of wonder. Let us slowly begin to explore why. To gently explore whether the universe could be a simulation, it helps to first soften into what modern physics reveals about reality itself. And what it reveals is far more mysterious and dreamlike than many people expect. The universe described by 20th and 21st century physics is not the solid, clockwork machine once imagined. Instead, it is subtle, fluid, and filled with surprising behavior that challenges our everyday assumptions. Let us begin with quantum mechanics, one of the most accurate yet most puzzling theories ever developed. Quantum mechanics describes how reality behaves at its smallest scales, the realm of atoms and subatomic particles. At this delicate level, the world does not follow the simple rules our senses are used to. Instead, it unfolds in ways that feel almost poetic, as if nature itself is whispering that reality is deeper than appearances. A classic example is the double-slit experiment. Imagine a device that sends out tiny particles, perhaps electrons, one at a time, toward a barrier with two very narrow openings. Behind this barrier is a screen that records where the particles arrive. When no one tries to observe which opening each particle passes through, the pattern that forms on the screen looks like the pattern made by waves overlapping, creating bands of light and dark. It is as though each particle travels through both openings at once and interferes with itself like a ripple in water. Yet when detectors are placed at the openings to check which path each particle takes, the wave-like pattern disappears. Instead, the particles behave like small solid objects going through one opening or the other. This gentle shift in behavior suggests that when unobserved, the particle exists in a state known as superposition, where multiple possibilities coexist. In this state, it does not have one single definite position. Only when a measurement occurs does this spread of possibilities settle into one actual outcome. This is not simply about our lack of knowledge. According to the theory, before measurement, the particle truly does not occupy a single definite state. It exists in a rich field of potential. This strange behavior is often described as wave-particle duality. Light and matter do not fit neatly into our old categories. They're not just waves and not just particles. There's something more subtle that can appear wave-like in one context and particle-like in another. Our words are only approximations, gentle metaphors for a reality that slips beyond familiar images. The role of observation here is one of the great mysteries of science. What exactly counts as an observation? Does it require a conscious mind, or is any interaction with a measuring device enough? Different interpretations of quantum mechanics offer different answers. The commonly taught Copenhagen view suggests that measurement causes the spread of possibilities to settle into a single actual event. Yet what truly qualifies as a measurement remains open to discussion. Some thinkers have even wondered whether consciousness itself plays a role. If that were so, awareness would not merely observe reality, but participate in shaping it at the most basic level. This idea has an intriguing resemblance to certain versions of the simulation hypothesis. In a simulated environment, fine details might only be calculated when needed, similar to how a video game renders only what the player can see. There is also the measurement problem, a puzzle that invites quiet reflection. The equations of quantum mechanics say that systems can remain in superposition, but measuring devices are also made of quantum particles. Why then do we not see measuring devices in fuzzy superpositions? Why do our experiences appear definite and stable? Various interpretations attempt to answer this. The many worlds view suggests that all possible outcomes occur, each in its own branch of reality. When a measurement is made, the universe gently divides into multiple versions, each containing a different result. In this picture, nothing truly collapses. Instead, reality continually unfolds into many parallel histories. Another approach, called decoherence, explains that interaction with the surrounding environment causes quantum possibilities to lose their delicate coherence. The strange behavior becomes spread out and effectively hidden, giving rise to the solid and predictable world we experience. In this account, the appearance of collapse emerges naturally from complex interactions, without requiring any special mechanism. What is remarkable is that these interpretations, though very different in their stories about reality, lead to the same experimental predictions. Mathematically, they agree, yet philosophically, they paint very different pictures of what is truly going on. Is there one definite world that settles into clarity when observed? Are there countless parallel worlds branching endlessly? Or does classical reality simply emerge from deeper quantum processes through interaction? The fact that we do not yet know shows us something important. Even our best physical theories leave the deepest nature of reality open. This gentle uncertainty creates space for many possibilities, including the idea that the universe might be based on information or computation, unfolding in ways that resemble a vast and subtle simulation. Another quantum phenomenon, known as entanglement, adds to this sense of wonder. When two particles become entangled, they form a single shared system, even if they later move far apart. If you measure one and find it in a certain state, you instantly know the state of the other. This connection appears to transcend distance. Before measurement, neither particle has a definite state, yet their possibilities are linked. When one settles into a specific outcome, the other does as well, in a perfectly correlated way. This effect does not allow signals to travel faster than light, yet reveals that reality is not purely local. Distant parts of the universe can be connected in ways that do not fit our ordinary picture of space as a simple separating stage. In a purely physical view, this non-local connection feels mysterious. But if reality is fundamentally about information, then distance might be more about how information is arranged than about absolute separation. From this perspective, deep connections across space may be less surprising. As we rest with these ideas, modern physics begins to look less like a story about tiny solid objects and more like a story about relationships, probabilities, and information. Reality at its roots appears fluid, contextual, and full of potential, becoming definite through interaction and observation. It is hard not to notice gentle parallels with computational systems, where data can exist in multiple possible states, where accessing information can change it, and where relationships between elements are often more fundamental than the elements themselves. None of this proves that we are living in a simulation. Yet it does show that the foundation of reality is far stranger and more subtle than everyday intuition suggests. And simply sitting with that strangeness, allowing it to soften our rigid assumptions about what is real, can be a deeply calming and expansive experience. As we continue this calm exploration, we turn gently toward the relationship between physics and information. If we want to sense whether the universe could be a simulation, it helps to understand that many modern physicists now view information not as a side note, but as something deeply woven into the fabric of reality itself. Over the past several decades, this perspective has grown steadily, like a quiet shift in how we understand existence at its most basic level. Information theory, first developed by Claude Shannon in the 1940s, offers a clear mathematical way to think about information. At its heart, information is about distinguishing between possibilities. A single bit, the basic unit of information, represents a choice between two options, such as 0 or 1, yes or no. From these simple distinctions, vast and intricate structures of information can be built. What is especially fascinating is that many physicists believe information, in this precise sense, is conserved in the universe. Just as energy is not created or destroyed, but only transformed, information too appears to follow a similar rule. This principle, often called unitarity or information conservation, is built into the fundamental equations of quantum mechanics. But what does it really mean to say that information is conserved? It suggests that if one knew the complete state of a physical system at a given moment, then in principle one could determine its state at any other moment, whether in the future or the past. Information about what has been is still present in what is, and the present contains within it the seeds of what will come. At the deepest level, the universe may be reversible and orderly in its evolution, even though at our everyday scale it appears full of chance and unpredictability. Seeing physics through this informational lens leads to beautiful and far-reaching ideas. The physicist John Archibald Wheeler expressed this with a phrase it from bit. He suggested that every physical thing, every particle and field, ultimately arises from basic yes or no distinctions. In this view, information is not merely a description we apply to the world. Information is the underlying reality. Matter and energy become patterns in a vast informational process, like shapes formed by currents in a flowing stream. One of the most surprising developments connected to this view is the holographic principle. In the 1990s, physicists studying black holes encountered a remarkable insight. The maximum amount of information that can be stored in a region of space appears to be proportional not to its volume, but to the area of its boundary. Imagine a sphere floating in space. Intuition suggests that the larger its volume, the more information it could contain. Yet the equations indicate that the true limit depends on the surface area instead. This idea is called holographic because of its similarity to holograms, where a three-dimensional image is encoded on a two-dimensional surface. In a similar way, the holographic principle suggests that everything happening inside a region of space could be described by information stored on the boundary surrounding it. All the particles, fields, and quantum states within a volume might have an equivalent description in terms of data on a distant surface. This concept first arose from attempts to understand black holes. When matter falls into a black hole, it seems at first that information about that matter could be lost forever. That would conflict with quantum mechanics, which says information must be preserved. Stephen Hawking once argued that information truly was destroyed in black holes, creating a deep puzzle known as the information paradox. Other physicists, including Leonard Susskind and Gerard T. Hooft, propose that the information is not lost but somehow encoded on the black hole horizon, its surface. Out of this debate grew the holographic principle. What is even more astonishing is that versions of this principle seem to apply not only to black holes, but to the universe as a whole. Our familiar three-dimensional world, with all its richness and complexity, might be fully describable by information on a distant cosmic boundary. The three-dimensional interior and the two-dimensional boundary could be two equally valid ways of describing the same underlying reality, connected by deep mathematical relationships. If the universe is fundamentally informational, this has general implications for the simulation idea. If everything can be described in terms of bits and their transformations, then reality already has a computational character. The difference between a physical universe and a simulated one begins to blur. If physics itself is a kind of information processing, then asking whether the universe is simulated becomes a subtler question. A mathematical process simply unfolds according to its rules, whether we call it physical or computational. In computer science, there's an idea known as the Church-Turing thesis. In simple terms, it says that any process that can be calculated by clear rules can be performed by a universal computing machine, at least in principle. Extended versions of this idea suggest that any physical process might be simulated by such a machine, given enough time and resources. If this is true, then in theory, even an entire universe could be reproduced step by step within a sufficiently powerful computational system. This leads naturally to a quiet and intriguing question. How much information can our universe contain, and how much processing has it performed? Physicists have made estimates based on the amount of matter and energy in the observable universe and its age since the Big Bang. These calculations suggest that the observable universe can hold on the order of 10 to the power of 90 bits of information and may have carried out around 10 to the power of 120 fundamental operations. These numbers are almost beyond imagination, yet they are finite. In this sense, the universe could be viewed as an immensely powerful but still limited information processing system. What might it be computing? In one gentle sense, it is computing its own unfolding. The present state of the universe, together with the laws of physics, gives rise to the next state. Moment after moment, the cosmos evolves according to its rules, as though performing an ongoing calculation. Whether we describe this as physical evolution or computation, the boundary between the two becomes softer and less distinct. The concept of entropy forms another bridge between physics and information. In thermodynamics, entropy is often described as a measure of disorder or the spreading out of energy. In information theory, entropy measures how much information is needed to describe a system. These two meanings are deeply connected. Ludwig Boltzmann showed that thermodynamic entropy is essentially about counting possible microscopic arrangements, which is another way of talking about information. The arrow of time. The reason that certain processes happen in one direction and not the other is closely related to how information becomes distributed and harder to track. Black holes play a special role here. For a given size, black holes have the highest entropy of any known objects, meaning they can contain enormous amounts of information. A black hole with the mass of our sun has an entropy of roughly 10 to the power of 54 bits. According to the holographic principle, this information is associated with the area of the black hole horizon. The larger the surface, the more information it can encode. When something falls into a black hole, the information about it is not thought to vanish. Instead, it becomes extraordinarily scrambled, woven into extremely complex correlations on the horizon. From the outside, it is effectively impossible to reconstruct the original details. The information still exists in principle, but accessing it would require unimaginable precision and resources. Some physicists suggest that as black holes slowly evaporate over immense timescales, the information they contain is eventually released in an extremely scrambled form through Hawking radiation. In theory, nothing is lost, but in practice, the information is so dispersed that recovering it would be far beyond any realistic capability. This deep interplay between information, entropy, and physical law hints that the universe operates as much through information processing as through forces and particles. Quantum theory can be framed in informational terms. Thermodynamics is tied to information. Even space and time themselves may emerge from more fundamental informational relationships. There are speculative approaches known as digital physics that take this idea very seriously. Thinkers such as Edward Fredkin and Stephen Wolfram have suggested that at its deepest level, the universe might be like a vast computational system following simple underlying rules. From repeated application of these rules, all the complexity of particles, fields, and galaxies could emerge. Wolfram has studied simple computational models called cellular automata, where basic units follow straightforward update rules. Despite their simplicity, some of these systems generate astonishingly rich and intricate patterns. He has proposed that something similar might underlie our universe, with space, time, and matter arising from a simple computational substrate operating at a fundamental level. These proposals remain speculative, and many scientists remain cautious. Yet they show how seriously the idea of information and computation as fundamental aspects of reality is taken in modern thought. Whether or not the universe is literally a programmed simulation, it behaves in many ways like an immense information processing system. Simply resting with that possibility, allowing it to gently expand our sense of what reality might be, can open a wide and calming perspective on the cosmos and our place within it. Let us now drift gently into the philosophical perspective that brought the simulation idea into serious modern discussion. In 2003, the philosopher Nick Bostrom presented what is now known as the simulation argument. This argument is subtle and carefully structured, and taking time to understand it can feel like slowly turning a crystal in soft light, seeing different facets reveal themselves one by one. Bostrom does not claim that we are definitely living in a simulation. Instead, he suggests that at least one of three possibilities must be true. This structure is known as a trilemma, a situation with three options where we may not know which is correct, yet logic tells us that at least one must hold. The first possibility is that civilizations like ours almost never reach the level of technology required to create realistic simulations of conscious minds. Perhaps most civilizations destroy themselves through war or environmental collapse before becoming so advanced. Perhaps there are fundamental limits in physics that prevent such simulations from ever being built. Or perhaps there are other unknown barriers that consistently stop intelligent life from reaching that stage. The second possibility is that some civilizations do reach this level of technological power, but for various reasons they choose not to create large numbers of simulations containing conscious beings. They might develop ethical principles that forbid creating simulated minds capable of suffering. They might lose interest in such projects or direct their immense computational resources toward other goals. The third possibility is the most startling. If many civilizations do reach the ability to run detailed simulations of conscious beings, and if they choose to run them in large numbers, then simulated minds would vastly outnumber original biological ones. A single advanced civilization could create countless simulated worlds, each filled with billions of conscious individuals. In that case, the overwhelming majority of conscious experiences would belong to simulated beings. From a simple probabilistic perspective, any randomly selected conscious observer would be far more likely to be in a simulation than in the original base reality. It is helpful to pause with this reasoning. The argument does not force the conclusion that we are simulated. Rather, it says that either advanced civilizations almost never achieve such technology, or they achieve it, but almost never use it to create conscious simulations, or we're probably already inside one. At least one of these must be true, even if we do not know which. This line of thought depends on several important assumptions. One key idea is that consciousness could arise in a non-biological system. That subjective experience does not depend strictly on organic neurons, but could emerge from the right kind of information processing. This view is known as substrate independence. Many researchers in cognitive science and philosophy of mind consider it plausible that what truly matters for consciousness is the pattern and organization of processing, not the specific material it runs on. If that is so, then a sufficiently advanced computer system could in principle host conscious experiences just as a biological brain does. Another assumption is that simulating consciousness does not require impossibly vast resources. A detailed simulation might not need to model every individual atom, but only the functional processes that give rise to thoughts, perceptions, and feelings. While this could demand extraordinary computational power, it may still lie within the reach of a highly advanced civilization. When we look at the history of technology, this idea becomes easier to imagine. For decades, Computing power has grown at an extraordinary rate. Machines that once filled rooms now fit in the palm of a hand, and supercomputers can model complex systems with billions of interacting elements. Neural networks inspired by the brain already contain enormous numbers of connections, and progress continues. If such growth were to continue over centuries or longer, the capabilities of future civilizations could be far beyond anything we currently picture. They might simulate not only individual minds, but entire societies within richly detailed virtual environments. They might run countless variations, exploring different histories, cultures, or physical conditions. If simulations of this kind became common, the probabilistic reasoning becomes striking. Imagine that for every original civilization, there are thousands of simulated versions, each containing billions of conscious beings. The number of simulated minds would then vastly exceed the number of original biological ones. In such a situation, the chance that you happen to be in the original layer of reality would be extremely small. There's also a gentle but important point here. Even if we were in a simulation, that would not make our experiences meaningless or unreal. If consciousness truly exists, if there is genuine inner experience, then that experience is real in the most direct sense. The fact that it might be implemented in a computational system rather than in biological tissue would not diminish the reality of joy, curiosity, or awareness itself. Another intriguing aspect of this idea is the possibility of layers. If our world is a simulation created by a more advanced civilization, then that civilization might itself exist within another simulation. This layering could, in principle, extend through many levels. We might be in a simulation within a simulation, part of a long chain of realities nested within one another. Bostrom suggests that this chain may not go on forever. Detailed simulations require resources, and each level would depend on the level above. At some point, there may be a foundational layer, a base reality that is not itself simulated. Yet from inside any given level, there may be no clear way to tell where one stands in this hierarchy. Each layer could feel just as solid and consistent as the next. Not everyone finds the simulation argument persuasive. Some philosophers point out that we currently have no direct evidence that we are in a simulation. Others question whether consciousness truly can arise from computation alone. Some argue that sufficiently advanced and ethical civilizations might avoid creating simulated beings who could suffer. Others suggest that simulated worlds might display detectable limitations or anomalies. Yet there are also thinkers who find the argument compelling, or at least difficult to dismiss. The philosopher David Chalmers, for example, has suggested that even in a simulated universe, our knowledge and science could still be valid. Our theories would describe the regularities of our world, whether that world is fundamental or implemented within a deeper level of reality. What makes the simulation idea philosophically powerful is that it is not purely fantasy. In principle, certain discoveries could support it, such as clear evidence of computational limits built into nature or unmistakable signs of underlying code like structure. On the other hand, if it turned out that consciousness depends on processes that cannot be reproduced by computation, the hypothesis would be greatly weakened. For now, we remain in a space of uncertainty. The simulation argument invites us to consider, with calm and open curiosity, that what once seemed like science fiction may be a genuine possibility grounded in reasoning about technology, probability, and the nature of mind. Whether or not it is true, reflecting on it can gently expand our sense of what reality might be. Now, let us wander through a different kind of territory features of our universe that some people view as suggestive, in a loose and speculative way, of a simulated reality. Right from the start, it is important to keep our feet on the ground. None of what follows counts as proof. Every point has conventional scientific explanations that do not require simulation at all. But if we temporarily entertain the idea, these features take on an interesting new flavor, like familiar scenery seen under unusual lighting. Begin with the deep mathematical structure of physical law. The universe does not just behave approximately mathematically, it obeys mathematical relationships with astonishing precision. The same equations that describe an apple falling from a tree also describe the motion of galaxies and the bending of space-time around black holes. Physicists have long been struck by this. Eugene Wigner famously called it the unreasonable effectiveness of mathematics. Why should abstract symbols scribbled on paper map so perfectly onto the workings of the cosmos? If reality were fundamentally messy or only loosely ordered, mathematics might still help us model it roughly, the way statistics models weather. But instead, nature seems to follow clean, elegant equations as if the universe itself were written in mathematical code. From a simulation perspective, this makes intuitive sense. A simulation must run on algorithms' precise mathematical procedures that compute outcomes from rules. The lawful regularity of physics could reflect the underlying computational rules of a vast program, with elegance emerging from efficient code rather than mystical necessity. Next, consider quantization, the discovery that at very small scales, nature comes in discrete chunks. Energy is not infinitely divisible, but appears in packets called quanta. Angular momentum, electric charge, even certain aspects of fields are quantized. Many physicists suspect that space and time themselves may have a smallest meaningful scale, known as the Planck length and Planck time. Below those scales, the concepts of distance and duration may simply lose meaning. That picture resembles digital computation more than classical, continuous physics. Computers do not operate on smooth continua, they process discrete bits. A simulated universe would naturally have a smallest unit of resolution, just as a digital image has pixels and a video has frames. The Planck length could be analogous to a spatial pixel, the smallest addressable unit of space. The Planck time could be like a cosmic frame rate, the smallest tick of the universal clock. Of course, this might just be how fundamental physics works, with no computer involved at all, but the parallel is hard to ignore once you notice it. Then there's the puzzle of fine-tuning. The constants of nature, the strengths of forces, particle masses, the cosmological constant seem to fall within extraordinarily narrow ranges that allow complex structures to exist. If gravity were slightly stronger or weaker, stars might not form in a stable way. If the electromagnetic force were different, chemistry as we know it might be impossible. If the cosmological constant were much larger, the universe might have expanded too quickly for galaxies to ever coalesce. One response is the anthropic principle: we see a life-permitting universe because only such a universe can contain observers. If there are many universes with different constants, a multiverse, then it is not surprising that at least one looks like ours. But from a simulation angle, another possibility appears. Perhaps the constants were chosen, not randomly, but deliberately set to produce rich complexity. This does not have to imply a divine creator. It could point to advanced simulators selecting parameters the way a game designer tunes the physics of a virtual world to make it interesting, stable, and full of emergent structure. Cosmology offers another curious feature: the horizon problem. When we look at the cosmic microwave background radiation, we see that regions of space on opposite sides of sky have almost identical temperatures. Yet according to simple models of the early universe, those regions were never in causal contact light, and heat would not have had time to travel between them. How, then, did they agree on the same temperature? The standard explanation is cosmic inflation, a brief period of extremely rapid expansion that smoothed things out before stretching space enormously. Inflation is well supported in many ways, but it introduces its own open questions about why it started and stopped as it did. In a simulation framing, one might imagine the early universe beginning from a set of clean, uniform initial conditions, a programmed starting state rather than a purely dynamical outcome. Again, this is not evidence, but it shows how simulation thinking can reinterpret existing puzzles. Consider also the speed of light. It is not merely the speed of light itself that is special, but the fact that it is the maximum speed at which information or causal influence can travel. No signal, no interaction can outrun it. In computational terms, this resembles a bandwidth limit or a maximum update rate. A simulation might impose a universal speed limit to ensure consistent, synchronized processing across its grid. The speed of light could play a role analogous to a system's clock speed, setting the pace at which cause and effect propagate. Relativity adds an even stranger twist. According to special relativity, simultaneity is not absolute. Two events that appear simultaneous in one frame of reference may occur at different times in another. There is no single cosmic now shared across the universe. From a computational perspective, this is oddly efficient. A simulation might not need to update the entire universe in lockstep. Instead, only causally connected regions would need consistent ordering, while distant, causally disconnected events would not require a single universal timestamp. Reality, in this view, is computed locally with relational consistency rather than globally with a master clock. Now think about the Fermi paradox, the question of why. In a galaxy with hundreds of billions of stars and billions of years of history, we see no clear evidence of other advanced civilizations. Even with relatively slow interstellar travel, a determined civilization could spread across the galaxy in a fraction of cosmic time. So where is everyone? There are many serious scientific proposals. Life may be rare, intelligence may be unlikely, civilizations may tend to self-destruct, or advanced beings may choose to remain quiet. But in a simulation framework, another possibility appears. Perhaps the simulation is focused on our planet or local region. Just as a video game renders high detail only where the player is looking, while distant areas are simplified or left unrendered, perhaps our universe includes us as the primary point of interest. Other civilizations might simply not be instantiated because they are not needed for the narrative or purpose of this particular simulation. It is a slightly unsettling thought, but it does offer a novel resolution of the silence. There is also the remarkable role of symmetry in physics. The laws of nature are built around deep symmetries, rotational symmetry, translational symmetry, gauge symmetries. Noether's theorem tells us that these symmetries are directly linked to conservation laws. Because the laws do not change over time, energy is conserved. Because they do not depend on location, momentum is conserved. These symmetries are not decorative, they are foundational. From a computational standpoint, symmetry is a gift. Symmetrical systems require less information to describe and can be simulated more efficiently. If the same rules apply everywhere and everywhen, the underlying program can reuse the same code rather than computing everything from scratch. The universe's symmetrical elegance might reflect not only deep physical truth, but also computational economy. Stepping back, caution is essential. Every one of these features has explanations within standard physics that do not involve simulations. Mathematical lawfulness may be an intrinsic feature of reality. Quantization may be fundamental rather than digital. Fine-tuning may be explained by multiverse theories. The Fermi paradox may have biological or sociological answers we have not yet discovered. Yet when viewed together, these aspects of our universe sketch a pattern that is at least compatible with the idea of a computational foundation. The cosmos appears mathematical, discretized at small scales, governed by information limits, structured by symmetries, and strangely well suited for complexity and observers. None of this proves we live in a simulation, not even close. But it does mean that the hypothesis fits more comfortably alongside modern physics than pure intuition might suggest. At the very least, it invites us to keep an open mind about just how deep the rabbit hole of reality might go. When we lift our gaze from everyday life and think about the universe on its largest scales, we encounter a landscape filled with deep mysteries. These are not small gaps in our knowledge, but vast open questions about why reality has the structure it does. Whether or not one takes the simulation idea seriously, these features of the cosmos invite a kind of philosophical pause. They make us wonder what sort of underlying framework could give rise to a universe like this one. We touched earlier on the horizon problem, but it deserves a slower and more careful look. When scientists study the cosmic microwave background, they're looking at light that has been traveling toward us for almost 14 billion years. This faint glow comes from every direction in space and carries with it a picture of the universe when it was very young, long before stars and galaxies had formed. What is astonishing is how uniform this radiation is. The temperature of the early universe, as revealed by this light, is nearly identical in all directions. The differences are tiny, about 1 part in 100,000. That level of smoothness is difficult to explain. Regions of space that are now extremely far apart, so far that light would not have had time to travel between them since the beginning of the universe, nevertheless share almost exactly the same temperature. According to the simplest version of cosmic history, those regions were never in contact. They could not exchange energy or information. So how did they come to agree so precisely on their physical conditions? How did the early universe manage to be so well coordinated across such enormous distances? The leading scientific answer is cosmic inflation. In this picture, the universe underwent an extremely brief period of explosive expansion in its earliest fraction of a second. Before that expansion, the regions we now see as widely separated were once close together. They had time to come into thermal balance. Then inflation stretched space so dramatically that those once neighboring regions were carried far beyond each other's horizons. The smoothness we observe today would then be a frozen imprint of that earlier contact. Inflation is elegant and powerful, but it opens new questions. It depends on the existence of a special field, often called the inflaton, with very particular properties. This field must have had just the right kind of energy and just the right behavior to drive rapid expansion and then to decay in a way that filled the universe with matter and radiation. We do not yet know what this field really is or why it had those properties. In a sense, the mystery is moved back a step rather than fully dissolved. If one looks at this from a simulation perspective, a different interpretation becomes imaginable. Instead of a physical process that smoothed out the universe, perhaps the smoothness reflects initial conditions chosen at the start. In a computer program, You can simply set the starting values of a system to be uniform. You do not need a prior physical mechanism to bring them into balance. The universe could have been initialized in a low entropy, highly ordered state because that was the desired starting configuration. This does not prove anything, and it does not remove the need for deeper explanation. It simply shifts the question to why those initial conditions were selected. But at some level, every account of the universe begins with conditions that are simply given. Whether we speak of an inflating field or of programmed initial data, we eventually reach a point where we say, this is how it started. Now consider dark matter and dark energy, two components that together make up about 95% of the total mass and energy of the cosmos. Everything we see, every star, planet, cloud of gas, and living being account for only a small fraction of what is out there. Dark matter reveals itself through gravity. Galaxies rotate so quickly that they should fly apart if only visible matter were holding them together. Clusters of galaxies bend light from more distant objects more strongly than ordinary matter alone would allow. The large-scale patterns in the cosmic microwave background also point to an invisible form of matter that outweighs the familiar kind. Yet this dark matter does not emit or absorb light. It seems to pass through ordinary matter almost without interaction. Despite decades of careful experiments, we have not directly detected the particles that might make it up. Dark energy is even stranger. Observations of distant supernovae and of the large-scale structure of the universe show that cosmic expansion is accelerating. Space itself is stretching faster and faster. Something is acting like a repulsive influence on the largest scales, overcoming the attractive pull of gravity. We call this influence dark energy, but the name is more a label for our ignorance than an explanation. The simplest idea is that dark energy is a cosmological constant, a tiny energy density inherent in empty space. But when physicists try to calculate such an energy using quantum theory, they get a value that is enormously larger than what we observe, off by a factor of about 10 to the power of 120. Reconciling theory and observation here is one of the most serious unsolved problems in fundamental physics. From a simulation-oriented point of view, it is tempting to see dark matter and dark energy as something like hidden infrastructure. In many complex simulations, there are background systems that keep everything stable and consistent. These systems are not directly visible to the characters inside the simulation, but they shape how the world behaves. One might imagine dark matter as a way of generating the gravitational scaffolding needed for galaxies to form without simulating every underlying detail in the same way as visible matter. Dark energy might be a global parameter that controls how the simulated universe expands over time. This is, again, speculative. There may well be entirely physical explanations for both dark matter and dark energy that fit comfortably within an eventual deeper theory. But the fact that most of the universe is made of components that we cannot see and do not yet understand does add a layer of strangeness when we step back and reflect on the overall picture. Another intriguing idea from theoretical physics is cosmic censorship. The equations of general relativity predict singularities, places where density and curvature become infinite and our known laws of physics break down. Black holes appear to contain such singularities, and the Big Bang itself, when traced backward in time, also leads to a singular state. Cosmic censorship is the proposal that these singularities are always hidden behind event horizons. We cannot observe them directly. Any breakdown in the laws of physics is sealed off from the rest of the universe. From our perspective, The horizon acts like a boundary beyond which we cannot see or receive information. In computational terms, singularities resemble points where a calculation would fail, where values would become undefined. A well-designed simulation might include mechanisms that prevent such problematic regions from affecting the rest of the system. Hiding singularities behind horizons could be seen as a way of containing regions where the usual rules no longer apply, ensuring that the broader simulation remains stable and predictable for its inhabitants. Time itself presents another deep puzzle. Most of the fundamental equations of physics do not care about the direction of time. They work just as well if you run them forward or backward. Yet our lived experience has a clear direction. We remember the past, not the future. We see eggs break and mix, but never spontaneously unmix and reassemble. This directionality is tied to entropy. The second law of thermodynamics tells us that entropy, a measure of disorder, tends to increase over time in a closed system. The future is the direction of higher entropy. But this leads to a profound question. Why did the universe begin in a state of such low entropy that there was room for entropy to increase? A high entropy universe would be far more typical. Yet our cosmos started in an extraordinarily ordered state. Inflation may help explain some aspects of this, but it does not fully solve the puzzle. The initial conditions of the universe still appear remarkably special. From a simulation perspective, the arrow of time might reflect the way the simulation is run. Perhaps the system computes each moment from previous ones, storing a record of the past, while the future remains uncalculated. The low entropy beginning would then be a deliberate starting point, chosen to allow complex structures and interesting histories to unfold. Finally, there's the holographic principle, a surprising idea emerging from attempts to unify gravity and quantum mechanics. In some formulations, all the information contained within a region of space can be described by data encoded on its boundary. Applied to the universe as a whole, this suggests that everything we see within our observable cosmos might be fully described by information on a distant surface, a kind of cosmic horizon. If that is true, then our three-dimensional world could be equivalent to a two-dimensional description at a deeper level. We would be like patterns in a hologram, experiencing a rich volume of space that, in a more fundamental sense, is encoded on a surface. This view does not automatically imply a simulation, but it does make reality seem more like an information processing system than a collection of solid, independently existing objects. Taken together, these cosmological features form a tapestry of unresolved questions. The smoothness of the early universe, the dominance of dark components, the hidden nature of singularities, the arrow of time, and the holographic hints about information and space all point to a cosmos that is subtle and layered. Conventional physics may ultimately account for all of them in a unified framework we have yet to discover. Still, it is understandable that some people see in these patterns a universe that looks less like a simple mechanical system and more like a vast, structured computation unfolding according to rules that may run deeper than space and time as we know them. Now we come to a mystery so intimate that it is easy to overlook how strange it truly is. Before galaxies, before physics, before simulations or base realities, there is the simple fact that experience exists at all. Any serious reflection on simulated worlds eventually runs straight into this question. Could consciousness, the felt sense of being, exist inside a simulation? And to approach that, we first have to sit quietly with what consciousness actually is. Right now, there's something it feels like to be you. You're not just processing information the way a calculator does. You see colors with a certain vividness. You hear sounds that have texture and tone. You feel sensations in your body, subtle or strong. Thoughts arise, emotions shift, memories echo. All of this is accompanied by an inner glow of awareness, a first-person point of view. Philosophers call this phenomenal consciousness, the raw felt aspect of experience. This is the one fact you cannot doubt. You might question whether the world outside your mind exists as it seems. You might wonder whether your memories are accurate or whether your senses sometimes mislead you. But you cannot coherently doubt that you are having experiences. Even doubt itself is a kind of experience. This insight goes back at least to Descartes, who realized that while everything else might be uncertain, the existence of experience is undeniable. And yet, this undeniable reality is also profoundly puzzling. We do not understand how or why consciousness arises. This is what philosopher David Chalmers famously called the hard problem of consciousness. There are many problems about the mind that are difficult but seem solvable in principle. We can study how the brain processes visual information, how it stores memories, how it controls movement and language. These are sometimes called the easy problems, not because they're simple, but because they concern functions and mechanisms. The hard problem is different. It asks why any of this processing should be accompanied by experience at all. Why is there something it feels like to see red, to taste coffee, to feel pain or joy? Why are certain physical processes in the brain associated with a rich inner life, instead of occurring in total darkness, like the silent operations of a computer? Take the experience of color. When you look at a red object, you have a very specific sensation, a particular shade of redness that is immediately familiar. Science can describe the wavelength of red light, how it stimulates photoreceptor cells in your eyes, how electrical signals travel through the optic nerve, how different regions of the brain become active. But none of these descriptions seem to capture the redness itself, the way red looks from the inside. We can push this further with a thought experiment. Imagine two people who behave identically when it comes to colors. They both call stop signs red, grass green, and the sky blue. But suppose that their inner experiences are systematically swapped. Where one experiences red, the other experiences what you would call blue, and vice versa. As long as their behavior and language use match, there would be no outward sign of the difference. This inverted spectrum scenario suggests that subjective quality might float free from purely functional or behavioral facts. These raw subjective qualities are often called qualia. The painfulness of pain, the sweetness of sugar, the warmth of sunlight, the heaviness of grief, the sharpness of embarrassment. Each has a distinctive feel that seems accessible only from the inside. We can describe the physical processes correlated with them, but the feel itself seems to resist purely objective explanation. The philosopher Thomas Nagel highlighted this in his famous question about bats. Bats perceive the world primarily through echolocation, emitting high-frequency sounds and interpreting the returning echoes. We can study their brains, measure their behavior, understand the physics of sound. But we still do not know what it is like to be a bat, to experience the world through that alien sensory system. Consciousness always has a point of view, and that point of view cannot be fully captured from the outside. This creates a deep tension for science. Science is built on objective, third-person descriptions. It excels at describing structures, functions, and relationships that anyone can in principle observe. But consciousness is essentially first-person. It exists as lived experience. Bridging this gap between objective description and subjective feeling is one of the greatest unsolved challenges in philosophy and neuroscience. Different theories try to close this gap in different ways. Materialism claims that consciousness is entirely a physical phenomenon. According to this view, once we fully understand the brain, we will see how subjective experience arises from neural processes, just as we came to understand how life arises from chemistry. Dualism, by contrast, holds that consciousness is not reducible to the physical. Mind and matter are two fundamentally different aspects of reality. This view preserves the distinctness of experience, but struggles to explain how a non-physical mind could interact with a physical brain. Panpsychism takes a more radical route. It suggests that consciousness, in some very basic form, is a fundamental feature of the universe. Even elementary particles might have extremely simple experiential aspects. Complex minds like ours would then arise from combinations of these simpler forms of consciousness. This avoids the leap from non-conscious matter to conscious mind, but it raises difficult questions about how simple experiences combine into unified ones. One of the most discussed contemporary proposals is integrated information theory. This theory attempts to quantify consciousness in terms of how much a system integrates information into a unified whole. According to this framework, a system is conscious to the extent that its internal states form a tightly interconnected structure that cannot be broken down into independent parts without loss of information. Consciousness, on this view, is identical to a certain kind of informational structure. What is striking here is that such a theory is substrate independent. It does not matter whether the information is integrated in biological neurons, silicon circuits, or some other medium. If the right kind of structure exists, then consciousness exists. This idea fits naturally with the possibility of artificial or simulated minds. A sufficiently complex computer system, if organized in the right way, could in principle be conscious. This connects directly to the simulation question. If consciousness depends only on patterns of information processing, not on the specific material that carries them, then simulated beings could be genuinely conscious. A detailed simulation of a brain running on some advanced computational substrate might generate real experiences, real thoughts, real feelings. This position is often called functionalism. It claims that what matters for the mind is functional organization, the causal roles played by different parts of the system. If two systems have the same functional structure, processing inputs and producing outputs in the same internally organized way, then they would share the same mental states and the same conscious experiences, even if one is made of neurons and the other of transistors. Not everyone agrees. Some philosophers argue that biology might matter in a deeper way. Perhaps specific chemical or even quantum processes inside living cells are essential for consciousness. On this view, a purely digital simulation, no matter how detailed, would at best mimic the outward behavior of a conscious being without generating real experience. John Searle's Chinese room thought experiment was designed to challenge the idea that computation alone is sufficient for understanding or consciousness. In the scenario, a person who does not know Chinese sits in a room with a rule book that tells them how to respond to Chinese symbols. From the outside, the system appears to understand Chinese, producing appropriate answers. But the person inside is just following rules blindly. Searle argues that computers are like this, manipulating symbols without any real understanding or awareness. Supporters of artificial consciousness respond that the intuition may be misleading. The person in a room does not understand Chinese, but the entire system, including the rule book and the process, might. Likewise, individual components of a brain do not understand anything on their own, yet the organized whole gives rise to a conscious mind. The debate turns on whether consciousness can emerge from the right kind of organization, even if the basic parts are not themselves conscious in any familiar sense. All of this remains unsettled. We do not yet know whether consciousness is fully substrate independent or whether it requires some special features of biological matter. And this uncertainty is crucial for the simulation hypothesis. If consciousness absolutely requires biological processes that cannot be replicated computationally, then our own conscious experience would be strong evidence that we are not living in a computer simulation. But if consciousness is a matter of information and organization, then simulated beings could be just as conscious as biological ones. In that case, the fact that you have experiences would not tell you whether your brain is made of neurons in a base reality or patterns of computation in a deeper level of reality. There is also an important reassurance hidden in this discussion. Even if we were in a simulation, our experiences would still be real. Pain would still hurt. Joy would still feel good. Love, curiosity, fear, wonder, all would still have their full weight from the inside. Being simulated would not make your consciousness an illusion. It would only mean that the underlying medium of your mind is different from what you might have assumed. In this sense, the simulation hypothesis does not drain life of meaning. If anything, it highlights that what ultimately matters is experience itself, a conscious pattern of information capable of feeling and reflection is a locus of value no matter what physical or computational substrate supports it. Some have even speculated that a simulated existence might be more stable or longer lasting than a purely biological one. A sufficiently advanced civilization might preserve and maintain simulations long after their own physical environment has changed. Of course, this is pure conjecture, but it shows how deeply the question of consciousness intertwines with our ideas about survival, identity, and significance. When we ask whether consciousness can exist in a simulation, we are really asking what consciousness is at the most fundamental level. Is it a special product of living tissue, or is it a pattern that can, in principle, be realized in many different forms? Until we understand that, the simulation hypothesis remains open. And in exploring it, we are pushed to confront one of the most profound facts of all, that the universe is not only made of matter and energy, but also, somehow, of experience. Let us gently wander into some of the more unusual and lesser-known discoveries in physics, the kinds of findings that make the universe feel far stranger than everyday life would ever suggest. None of these phenomena prove that reality is a simulation, yet each one quietly reminds us that the foundations of the cosmos are already more mysterious than we tend to imagine. We can begin with quantum entanglement, a phenomenon we mentioned before, but one that deserves a slower and deeper look. When two particles become entangled, their properties become linked in a way that seems to ignore distance entirely. If you measure the spin of one particle, you immediately know the spin of the other, even if it is light years away. What makes this so remarkable is that the connection is stronger than anything allowed by classical physics. Physicist John Bell showed mathematically that no theory based on local hidden variables, where particles carry definite properties in advance and no influence travels faster than light, can reproduce the predictions of quantum mechanics. Careful experiments have repeatedly confirmed the quantum predictions. Nature truly behaves this way. This tells us that reality is not strictly local in the way we once believed. Things that are widely separated in space can still be deeply connected. Yet this connection cannot be used to send messages faster than light. The correlations appear instantly, but usable information still travels at or below light speed. It is as if the universe allows deep coordination without allowing direct communication, a subtle and delicate balance. From an informational point of view, entanglement hints that space itself might not be fundamental. Perhaps what we think of as distance is a secondary feature, emerging from more basic informational relationships. Entangled particles may be directly linked in this deeper layer, even if they appear far apart in ordinary space. Another experiment that invites quiet wonder is the delayed choice quantum eraser. This is a refined version of the famous double-slit experiment, and it seems at first to suggest that future choices can influence past events. In this setup, photons pass through two slits, and you arrange the apparatus so that you can later decide whether to preserve or erase information about which slit each photon passed through. Strangely, that later choice affects the pattern you observe. If which path information is available, the photons behave like particles. If it is erased, they produce an interference pattern, as if they had gone through both slits like waves. It can feel as though the photon somehow knew what you would decide in the future. In reality, the situation is more subtle. Quantum mechanics describes correlations between measurements rather than definite histories unfolding in a classical way. Still, the experiment gently loosens our usual sense of time and causation, suggesting that at the quantum level, reality does not follow the tidy sequence of past, present, and future that we experience in daily life. Now, let us consider virtual particles. According to quantum field theory, what we call empty space is not truly empty. It is filled with fields that are always fluctuating. These fluctuations can briefly give rise to particle and antiparticle pairs that appear for a tiny fraction of a second and then vanish again. We do not observe these virtual particles directly, yet their effects are measurable. They influence the behavior of real particles and contribute to phenomena like the Casimir effect, where two metal plates placed very close together in a vacuum feel a small force pulling them together. They also affect the magnetic properties of the electron, predictions that have been confirmed with astonishing precision. Virtual particles blur the line between something and nothing. They are not fully real in the ordinary sense, yet they are not mere abstractions either. They are temporary ripples in underlying fields, possibilities that briefly become actual before dissolving again. It is a vision of reality that feels less like solid objects and more like an ongoing process of calculation and fluctuation. Time itself becomes strange when we look closely. Einstein's theory of relativity teaches us that time does not flow at the same rate for everyone. Clocks moving at high speeds tick more slowly. Clocks deep in strong gravitational fields also run more slowly. These are not illusions. They are real, measurable differences. Modern technologies rely on this. The satellites that power global positioning systems must correct for relativistic time shifts. Without those corrections, navigation systems would quickly drift and become unreliable. Even our everyday tools quietly depend on the flexible nature of time. Yet relativity raises deeper questions. If time depends on motion and gravity, what does it really mean to say the universe has a specific age? Cosmology answers this by defining a cosmic time based on observers who move along with the general expansion of the universe. Still, it reminds us that time is not an absolute background stage, but part of the dynamic structure of reality. Some approaches to quantum gravity go further and suggest that time may not be fundamental at all. At the deepest level, the universe might be described by timeless equations, with time emerging only as an approximate concept that makes sense at large scales. In such a picture, the flow of moments we experience could be like temperature, a useful and real feature of large systems, but not present in the most basic description. There's also the quantum Zeno effect, a phenomenon with an almost meditative quality. In quantum mechanics, if you measure a system frequently enough, continually asking whether it is still in its initial state, you can slow down or even halt its evolution. Observation, repeated again and again, can freeze change. This effect has been confirmed in laboratories. It shows that measurement is not a passive act. It actively participates in shaping what happens. The line between observer and observed becomes soft, with awareness and interaction woven into the unfolding of physical processes. Vacuum energy presents another quiet mystery. Quantum field theory suggests that even empty space has a baseline energy, the so-called zero-point energy. When physicists try to calculate this energy, the result comes out unimaginably large. Yet when we look at the universe, the effective vacuum energy, which shows up as dark energy driving cosmic acceleration, is incredibly small. The mismatch between theory and observation is enormous, one of the largest known discrepancies in physics. Something in our understanding is incomplete. Either different contributions almost perfectly cancel, or our description of empty space needs a deeper revision. We can also reflect on the initial conditions of the universe. The early cosmos was astonishingly smooth and uniform, with only tiny variations in density. Those slight variations later grew into galaxies and stars. If the early universe had been a bit more uneven, matter might have collapsed too quickly into black holes. If it had been even smoother, structure might never have formed at all. The fact that the universe began in just the right state to allow complexity is still not fully explained. Inflation offers part of the story, but it too seems to require special conditions. We are left with a sense that the starting point of everything was delicately balanced in a way that invites reflection. All of these phenomena, entanglement, delayed choice effects, virtual particles, the flexibility of time, the quantum Zeno effect, vacuum energy, and finely tuned beginnings, reveal a universe that is already deeply mysterious. Reality at its foundations is subtle, relational, and often counterintuitive. Whether or not it is a simulation, it behaves in ways that feel closer to information processing than to the solid mechanical picture we once imagined. And simply resting with that strangeness can be a calming reminder that the universe is wider, softer, and more wondrous than our everyday assumptions. Let us continue by exploring some of the more exotic and lesser-known phenomena in physics, the kinds of discoveries that make reality seem far stranger than our everyday experience would ever suggest. These scientific curiosities do not prove that we're living in a simulation, but they do reveal just how deeply unusual the universe becomes when we look at its foundations. Begin with quantum entanglement, which we mentioned earlier, but which deserves a deeper and more careful look. When two particles become entangled, their quantum states become linked in a way that seems to ignore distance entirely. Measure the spin of one particle and you immediately know the spin of the other, even if they are separated by vast stretches of space. What makes this even more astonishing is that the connection between them is stronger than any classical form of correlation could ever be. Physicist John Bell proved this mathematically with what is now called Bell's theorem. His work showed that no theory based on local hidden variables, meaning theories where particles carry definite properties before we measure them and no influence travels faster than light, can reproduce the predictions of quantum mechanics. Experiments have repeatedly confirmed that quantum mechanics is correct. The implication is profound. Reality at its core is non-local. Things that are separated in space can still be connected in an immediate and fundamental way. And yet, this strange connection does not allow faster-than-light communication, which seems almost paradoxical. You cannot use entanglement to send message. The information exists in the correlations, but actually accessing it always requires ordinary communication that is limited by the speed of light. From an informational point of view, this is deeply intriguing. It suggests that the universe may be organized in ways that do not depend on spatial separation at the most basic level. Space itself might not be fundamental. Instead, space could emerge from deeper informational relationships, with entanglement acting as a kind of direct connection in an underlying network that later appears to us as geometry. Even stranger is the delayed choice quantum eraser experiment, a variation of the famous double-slit experiment that seems, at first glance, to involve effects happening before their causes. In this setup, photons are sent through a double-slit apparatus. The experiment is arranged so that you can decide, after the photon has already passed through the slits, whether to measure which path it took. Astonishingly, your later decision influences the pattern that forms. If which path information is available, the result looks like particles. If that information is erased, an interference pattern appears, as if the photon behaved like a wave. It almost seems as if the photon somehow knew in advance what you were going to choose. But this does not actually require backward causation. The resolution comes from understanding that quantum mechanics does not describe tiny objects with definite properties moving through space in the classical sense. Instead, it describes correlations between measurements. Still, the experiment highlights just how far quantum reality departs from our everyday intuitions about cause and effect. Now consider virtual particles, another remarkable feature of quantum field theory. According to this theory, empty space is not truly empty. It is filled with quantum fields that are constantly fluctuating. These fluctuations can briefly give rise to particle and antiparticle pairs that appear and then vanish again almost immediately. We cannot observe these virtual particles directly, but their effects are measurable. They help explain the Casimir effect, in which two metal plates in a vacuum experience a tiny force pushing them together. They also contribute to the magnetic properties of the electron, predictions of quantum electrodynamics that have been confirmed with extraordinary precision. Virtual particles blur the line between existence and non-existence. They do not exist in the ordinary, stable sense. If they did, they would violate conservation of energy. And yet they are not nothing. They are temporary fluctuations, fleeting possibilities that briefly manifest and then dissolve back into the restless quantum background of space. There's an interesting parallel here with computation. In computer programs, temporary variables often appear for just a moment during a calculation and then disappear once their job is done. Virtual particles resemble these fleeting computational elements, short-lived excitations used in the universe's ongoing processes and then removed. Now, shift attention to time itself. Einstein's theory of relativity tells us that time is not absolute. It flows at different rates for observers in different states of motion and in different gravitational fields. Time passes more slowly for objects moving at high speeds and for those deep in strong gravitational wells. These are not illusions or measurement errors. They are genuine differences in how much time actually elapses. The global positioning system must account for these relativistic effects. The clocks on GPS satellites tick at a different rate than clocks on Earth's surface because of both their speed and their position in Earth's gravitational field. Without correcting for this, GPS would quickly lose accuracy. Relativity also raises subtle questions. If time is relative, what does it really mean to say the universe is about 13.8 billion years old? The answer involves something called cosmic time, defined in the reference frame of the overall expansion of the universe. Galaxies that are at rest relative to the cosmic microwave background share this common measure of time. Even more mysterious is the possibility that time itself is not fundamental. Some approaches to quantum gravity suggest that time may emerge from deeper, timeless quantum relationships. At the most basic level, there might be no sequence of moments at all. Time could be like temperature, a large-scale property that appears only when many components interact, not something built into the deepest layer of reality. If time emerges from a timeless foundation, then causation, change, and the flow of experience all become subtle and unresolved puzzles. These questions remain open, but they hint that even time, perhaps the most intimate feature of our experience, might not belong to the ultimate structure of reality. Consider also the quantum Zeno effect. This is a phenomenon in which repeatedly observing a quantum system can prevent it from changing. If you measure a particle often enough, continually asking whether it is still in its original state, the very act of measurement can keep it there. Observation can effectively freeze evolution. The name comes from Zeno's ancient paradoxes about motion. Just as Zeno argued that motion seems impossible if an object must pass through infinitely many points, the quantum Zeno effect shows that continuous observation can inhibit quantum transitions. The system remains locked in place because it is being constantly checked. This effect has been demonstrated experimentally. It provides yet another example of how measurement in quantum mechanics is not passive. Observing a system does not simply reveal what was already there. It actively influences what happens. Now return to the idea of vacuum energy. Quantum field theory predicts that even empty space contains energy known as zero-point energy. When physicists calculate this energy by adding up all possible fluctuations of all quantum fields, they get an infinite result. They handle this using a technique called renormalization, which removes the infinities in a controlled way while preserving accurate predictions for measurable quantities. However, when we consider the total vacuum energy that should affect the expansion of the universe, we run into a major problem. The theoretical prediction is about 10 to the power of 120 times larger than what we observe. This is often called the worst theoretical prediction in physics. Why is the vacuum energy so incredibly small compared to what theory suggests? What cancels almost all of it, leaving just a tiny remainder that drives cosmic acceleration? We do not know. Many ideas have been proposed, from new symmetries to anthropic reasoning, but no explanation is completely satisfying. From a simulation viewpoint, this puzzle becomes intriguing. Perhaps vacuum energy is not a fundamental physical quantity at all, but an artifact of the way we describe the system. The underlying computational layer might not need to simulate vacuum energy in the same way. The small observed value could be more like a parameter in the simulation than a direct consequence of simulated quantum fields. Another curious feature of our universe is how finely tuned its initial conditions appear to have been. The early universe was extraordinarily smooth and uniform, with density variations of only about 1 part in 100,000. If it had been just a bit more clumpy, gravity would have caused it to collapse rapidly into black holes. If it had been even smoother, matter might never have clumped together to form galaxies, stars, and planets. The odds of starting in such a delicately balanced state seem extremely low. Cosmic inflation helps explain why the universe is so uniform, but inflation itself requires special initial conditions. We are still left wondering why the universe began in such a rare and structured state. Various explanations have been suggested, including multiverse scenarios, anthropic selection, and cyclic cosmologies. Or perhaps the initial conditions were in some sense chosen, whether by deeper physical principles or by simulators setting up a universe capable of producing complexity and life. All of these scientific oddities, non-local entanglement, delayed choice effects, virtual particles, the relativity of time, the quantum Zeno effect, vacuum energy, and finely tuned initial conditions point toward a universe that is far stranger than everyday common sense would suggest. At its foundations, reality looks less like solid matter and more like information, relationships, and probabilities. We should be careful not to overinterpret these phenomena. They are real physical effects that may eventually be understood in entirely conventional ways. Still, they show us that the universe is deeply mysterious, filled with unresolved questions. And they make the idea of a computational or simulated reality feel a little less absurd, because the world already defies our naive expectations in profound and surprising ways. Let's turn now to a crucial and deeply human question. Suppose we really are in a simulation. Would it actually matter? What would that mean for purpose, for ethics, for how we should live our lives from day to day? For some people, the first reaction is bleak. If we are simulated, if reality is in some sense artificial, if we're just patterns in a vast computational process, then nothing matters. Our lives would seem weightless, our struggles pointless, our joys hollow. This reaction is understandable. It comes from the feeling that only something physically fundamental can truly count. But that conclusion does not follow. Pause and consider what actually gives your experiences value. When you feel joy, when you fall in love, when you're moved by music or stand quietly watching a beautiful sunset, why do those moments matter? They matter because of how they feel from the inside. They have value because there is something it is like to be you in those moments. The worth of the experience lies in its subjective quality, not in the specific material that happens to support it. Let's look at this more carefully. Imagine the joy of reuniting with someone you deeply care about, or the quiet satisfaction of achieving a goal you worked toward for years, or the sense of awe when you look up at the night sky. What makes these experiences precious? Is it the exact arrangement of neurons firing in your brain? Or is it the felt quality, the inner richness, the lived experience itself? Most of us, when we reflect honestly, would say it is the experience itself that matters. The neural activity is important only because it gives rise to that experience. If this is true, then the underlying substrate is not what gives life its meaning. Whether your mind runs on biological neurons, on silicon circuits, or on some unimaginable medium, the joy is still joy. The love is still love. The wonder is still wonder. Think about stories. In a novel or a film, the characters are not physically real people. They are patterns of ink on a page or arrangements of pixels and sound. Yet their inner lives can feel meaningful to us. We cry for them, hope for them, learn from them. Now imagine those characters were not just fictional, but actually conscious, actually experiencing their struggles and triumphs from the inside. Their experiences would then have genuine value, even if their world were entirely artificial. Take Elizabeth Bennet from Pride and Prejudice. She is not made of flesh and blood. She exists as patterns in Jane Austen's writing, in readers' imaginations, in performances on stage and screen. And yet her journey feels meaningful. Her wit, her misunderstandings, her growth, her love, all of it resonates because it reflects a rich inner life. If Elizabeth were truly conscious, truly aware, then her experiences would be just as real and significant as anyone's in our world. The fact that her world was implemented in text rather than atoms would not make her suffering or her joy any less real to her. In the same way, if we exist in a simulation, our consciousness is still real consciousness. Our experiences still happen from the inside. The substrate does not determine whether an experience is real. It only determines how that experience is physically or computationally realized. In fact, discovering that we are simulated would leave most of what matters in daily life unchanged. You would still care about the people you love. You would still have goals, fears, hopes, and memories. You would still face choices about how to act, how to treat others, what kind of person you want to become. The ethical landscape would not suddenly disappear. If someone suffers, their suffering is still bad because it feels bad to them. If you're kind, your kindness still matters because it genuinely improves someone else's experience. Truth would still matter because having accurate beliefs helps conscious beings navigate their world more effectively. Being simulated does not erase ethics. It does not turn pain into nothing or joy into illusion. Philosopher David Chalmers has argued for a view sometimes called virtual realism. According to this idea, if we are in a simulation, the objects around us are still real objects. A table exists. A mountain exists. They are not made of what we thought they were made of, but they are still part of a consistent, law-governed reality. They are computational entities rather than arrangements of atoms in a deeper level of physics, but they are real within our world. The same goes for you. You would still be a real person, a genuine conscious being. Your thoughts would be real thoughts. Your emotions would be real emotions. You would not be a fake or an illusion. You would simply be implemented in a different way than you assumed. This means that even if we discover tomorrow that we are in a simulation, science would still function. Physics would still describe the regularities of our environment. Biology would still explain living processes within the simulation. History would still tell the story of what happened in our world. Our relationships would still be meaningful connections between conscious beings sharing a common reality. What might change is our sense of what is possible. If we are simulated, then there may be higher levels of reality beyond ours. There may be beings with access to the underlying system, capable of modifying parameters, pausing processes, or observing us in ways we cannot observe them. Some people imagine the possibility of hacking the simulation, finding glitches or loopholes that would allow us to manipulate reality from within. If the universe is computational, perhaps there could be exploits, ways of accessing deeper layers of the code. From inside, such events would look like miracles. From outside, they would just be system-level operations. But we have no evidence that anything like this is possible. A well-designed simulation would not expose its source code to the characters inside it. The apparent consistency and stability of physical law suggest that if we are in a simulation, it is a robust one with very few, if any, exploitable flaws. Now consider death in a simulated universe. If minds are fundamentally information patterns, then in principle they could be copied, preserved, or re-instantiated in new substrates. The end of a biological process inside the simulation would not necessarily mean the end of consciousness altogether. The simulators might keep backups. They might store the informational structure of conscious beings. When someone dies in the simulation, their pattern could be rerun elsewhere, perhaps in another simulated environment or at a higher level of reality. In such a scenario, death would not be absolute annihilation, but a transition from one domain to another. This is speculative, and we should not assume it is true. Still, it shows how a simulation framework could transform the way we think about mortality. What looks like an ending from within one layer of reality might be only a boundary in a much larger structure. There are also intriguing connections to religion and spirituality. Many traditions speak of higher realms, of beings beyond our world, of consciousness persisting after bodily death. In a simulation framework, these ideas might be reinterpreted as intuitions about the structure of reality. The simulators could resemble gods, not necessarily morally perfect or omnipotent, but vastly more powerful and knowledgeable than we are. Miracles could be interventions in the simulation. An afterlife could correspond to existence in another level of reality beyond our current one. This does not prove any particular religious view, but it shows that simulation and spirituality are not automatically in conflict. What about purpose and meaning? If we are simulated, does that mean our purpose is whatever the simulators intended? Or can we still create our own meaning? Even if the simulators had specific goals, your life's meaning is not dictated solely by their intentions. Your parents may have had certain reasons for bringing you into existence, but your life's meaning is not limited to their plans. In the same way, even if simulators had a purpose in creating our world, you are still a conscious being who can value things, form commitments, love others, and shape your own path. Meaning arises from engagement, from caring, from relationships, from striving toward things you find worthwhile. These sources of meaning do not vanish just because the deeper metaphysics of reality turns out to be different than you thought. Here is a strangely comforting thought. If we are in a simulation, and this simulation has already been running for billions of simulated years, then whoever runs it has allowed it to continue for a very long time. They have not simply switched it off. They have sustained a world containing stars, galaxies, life, and countless conscious experiences. That suggests that the continuation of the simulation has value to them. Of course, we cannot know how long it will last. The simulation could end suddenly from our perspective, but the sheer duration and richness of what has already unfolded hints at a kind of underlying stability, a deeper layer of reality that has supported our world for an immense span of time. Finally, consider science itself. If we are simulated, can we still trust our scientific discoveries? Are the laws of physics genuine or just programmed rules? Within our level of reality, those laws are completely real. They describe the regular patterns that govern our experiences. Whether those patterns arise from fundamental metaphysical necessity or from lines of code in a deeper system makes little difference to their reliability for us. Science would still uncover real regularities, still make accurate predictions, still deepen our understanding of our world. In fact, the mathematical elegance of physical laws might even fit naturally with the simulation idea. The universe is describable in compact equations. Its behavior is structured and lawful. That is exactly what we might expect if it were implemented computationally. A base-level reality without any computational constraints might be far messier and less mathematically tidy. The central insight is this: being simulated would not make our lives meaningless or unreal. It would change our understanding of what ultimately grounds reality, but it would not erase the reality of our experiences. We would still be conscious beings feeling real joys and real sorrows, making genuine choices, forming real relationships, and creating authentic meaning in the only world we directly know. As we reach the end of this long and thoughtful journey, we find ourselves standing before an even larger horizon. The question of whether we are living in a simulation has carried us through physics, philosophy, consciousness, meaning, and the deep structure of reality. It has stretched the imagination and challenged many of our quiet assumptions. But after exploring all of this, where does it leave us? What can we honestly say? The most truthful answer is simple and humbling. We do not know, and it is possible that we may never know with certainty. The simulation hypothesis remains a possibility, a lens through which we can examine reality, but not a conclusion we can firmly establish with the evidence we currently have. If we wanted proof that we are in a simulation, what would that even look like? We would need clear and unmistakable signs of the underlying system. Perhaps observable glitches in reality, hard limits where the simulation breaks down, or direct messages from whatever intelligence might be running it. Another path would be a compelling theoretical demonstration that reality must be computational at its deepest level. So far, we have neither. We do not see obvious glitches. The universe behaves in lawful and consistent ways. Quantum mechanics is undeniably strange, but it is a precise and reliable strangeness described by elegant mathematical structures. The cosmos does not appear to stutter or crash like a faulty program. If there are limits to resolution or hidden computational boundaries, they lie far beyond our current ability to probe them. We have not received messages from outside. There is no clear signal that beings beyond our universe are attempting to contact us. If simulators exist, they are silent, or their way of communicating is so far beyond our understanding that we cannot recognize it. On the theoretical side, there is no consensus that reality must be a computation. Some thinkers explore digital physics and information-based models of the universe, but these ideas remain speculative and far from universally accepted. Most scientific work proceeds without needing to assume that the cosmos is a simulation. So we find ourselves in a place of uncertainty. At first, this may feel frustrating, but it is also deeply meaningful. We are encountering the edge of knowledge, the place where our questions outrun our tools. This boundary has always been part of the human story. There is something profoundly human about asking questions we cannot fully answer. Ancient philosophers wondered about the ultimate substance of reality. Medieval thinkers reflected on the nature of creation and existence. Today, we ask whether the universe is computational. The language changes, the metaphors evolve, but the underlying curiosity remains the same. We are trying to understand what lies beneath appearances. It is even possible that the question is unanswerable in principle. Imagine a simulation designed so perfectly that nothing within it could ever reveal its artificial nature. Every experiment would return results consistent with an ordinary physical universe. Every observation would fit the internal rules. In such a case, no matter how advanced our science became, we might never be able to tell. This creates a curious situation. There is a fact of the matter. Either we are simulated or we are not. Yet we may have no reliable path to discovering which is true. The hypothesis might be unfalsifiable, beyond the reach of experiment or observation. Some would argue that such ideas should be ignored. If a claim cannot be tested, they say it has no place in serious inquiry. But this seems too narrow. Many of the most important human questions are not easily testable. Questions about consciousness, about moral value, about meaning in life, all resist simple experimental answers. Yet they remain central to our lives. In the same way, the simulation hypothesis can be meaningful even if it cannot be decisively confirmed or denied. It reshapes how we think about reality. It invites us to reconsider what we mean by physical, by real, by fundamental. It encourages intellectual humility and imaginative openness. There is also a recursive twist to all of this. If we're simulated, then perhaps our simulators are simulated too, and they're simulators in turn. This suggests a potentially endless chain, a stack of realities, each built upon another. Or perhaps there is a final layer, a base reality at the bottom of the chain. From where we stand, we cannot tell. We have no way to count the levels above us, or to determine whether we are at the foundation or somewhere far up the ladder. Philosophers have long explored similar possibilities. Descartes imagined a powerful deceiver manipulating his perceptions. Modern thought experiments describe brains in vats connected to artificial inputs. The simulation hypothesis is a contemporary version of these ancient worries about deception and illusion. Yet there is an important insight that survives all such scenarios. Even if everything you perceive is generated by a system outside your control, you are still having experiences. You still think, feel, hope, and wonder. Your consciousness remains undeniable from your own perspective. Even in the most extreme, skeptical scenario, the reality of experience itself cannot be erased. This may not answer the question of whether we are simulated, but it anchors us. It shows that while the outer structure of reality may be uncertain, the inner fact of experience remains firm. Whatever the ultimate nature of the universe, there is still something it is like to be you, right now. There is a strange kind of freedom in this uncertainty. We are not burdened with definitive knowledge that we are simulated, forced to reinterpret everything through that lens. Nor are we confined to the certainty that our level of reality is the absolute foundation. Instead, we live in a space of open possibility. Reality may be deeper and more layered than we imagine, or it may be fundamental and self-contained. Both remain live options. In everyday life, this uncertainty changes surprisingly little. You still wake up each morning. You still talk with friends, make plans, feel emotions, and face choices about how to live. The texture of experience, the flow of moments, remains the same. What changes is the background sense of mystery. The world may no longer feel like a closed and fully explained system. It may feel more like a surface, a visible layer over something deeper and unknown. For some, this sense of depth is unsettling. For others, it is inspiring. It makes existence feel larger, more open, more filled with wonder. Uncertainty does not have to be an enemy. It can be a companion, reminding us that we have not reached the end of understanding. It leaves room for curiosity, for imagination, for awe. The universe remains, in an important sense, unfinished from our point of view. In the end, perhaps the simulation question is not only about physics or metaphysics. Perhaps it is also about values. Do we most care about pinning down the ultimate structure of reality, or about the quality of the lives we live within it? Do we need to know the deepest layer in order to love, to create, to explore, to grow? For most of us, when we look inward, it is the lived experience that matters most. The depth of connection, the richness of feeling, the pursuit of understanding, the small acts of kindness and moments of beauty. These do not lose their importance if the universe turns out to be implemented in code rather than quarks. So the mystery remains. We do not know whether we are in a simulation, and we may never know. But this is not a failure. It is an invitation to humility and wonder. It reminds us that reality is larger than our current theories, that existence still holds secrets beyond our reach. And there's a quiet beauty in that. We are conscious beings, aware enough to question the nature of our own world, yet small enough to stand in genuine awe before it. Whether fundamental or simulated, the universe we experience is vast, intricate, and filled with the possibility of meaning. That, in itself, is something extraordinary. We have moved together through a long and gentle exploration of reality, consciousness, physics, and possibility, slowly wandering through questions that humans have asked for centuries and that modern science is only beginning to approach. Along the way, we have considered the idea that the universe could be a kind of simulation, looked at arguments that support or challenge that view, explored imaginative and speculative possibilities, and reflected on what it might truly mean if the world we experience is generated in ways far beyond our current understanding. Now, as this journey begins to soften towards close, it is time to gather these ideas calmly, to sit with what we have uncovered, and to notice the questions that still shimmer quietly at the edges of our understanding. At the heart of the simulation idea is a gentle invitation to reconsider our deepest assumptions about what is real. Most of us naturally assume that what we see and touch is the most basic layer of existence, that the physical world is the foundation of everything, and that consciousness somehow rises out of matter like a flame from a candle. The simulation perspective asks us to loosen our grip on these assumptions and to imagine other possibilities. It asks us to wonder whether the physical world could be more like information being processed, whether consciousness might be more central to reality than we once believed, and whether there could be layers of existence beyond anything our senses can currently reach. Simply allowing these questions into the mind can expand our sense of what might be true. Whether or not we are actually living in a simulation, spending time with this question has real value. It connects us to profound reflections about existence, about the nature of awareness, and about the mysterious relationship between mind and world. It gently lifts our attention beyond daily routines and small concerns, and opens a wider horizon filled with curiosity and quiet awe. There's something naturally meditative about contemplating these possibilities. When you imagine that reality might be informational at its core, that consciousness could extend beyond the limits of the body, or that there might exist beings or levels of intelligence far beyond our own, your perspective begins to shift. Worries that once felt overwhelming can start to feel smaller within a much larger and more mysterious picture. You begin to sense that you are participating in something vast, something that cannot be fully grasped but can be peacefully appreciated. This does not mean turning away from ordinary life or practical responsibilities. You still wake, move, choose, care, and act in the world. Yet holding these larger questions softly in the background can bring a sense of balance. It can remind you that life contains depths and dimensions beyond whatever is demanding your attention right now. As we reflect on what we have learned, we can remember that modern physics already shows us a universe far stranger than everyday intuition suggests. In the quantum world, observation and outcome are closely linked. Particles can be connected across enormous distances, and the line between possibility and actuality is more fluid than it first appears. We have also seen that information seems to play a fundamental role in the structure of reality, and that some theories suggest the three-dimensional world we experience could in some way be encoded more deeply, almost like a vast cosmic pattern of data. Philosophical ideas, such as the simulation argument, propose that advanced civilizations might create many artificial realities, which lead to the intriguing statistical suggestion that simulated worlds could outnumber original ones. We have looked at features of the universe that some people interpret through this lens, such as the mathematical elegance of physical laws, the discrete nature of energy and matter, the delicate balance of constants that allow life to exist, and the possibility that there are ultimate limits to how finely reality can be divided. We have also explored the mystery of consciousness itself, especially the deep challenge of explaining subjective experience, the feeling of being aware. Some thinkers suggest that consciousness might not depend on a specific physical material and could in principle arise in many kinds of systems, even simulated ones. From there, our imagination has stretched into more speculative territory, touching on ideas of nested realities within realities, universes that function as learning environments, the possibility that consciousness is a fundamental feature of existence, and even the thought that the past and future of the cosmos might be woven together in ways we do not yet understand. Through all these reflections, we have also considered the implications. Even if we were simulated, our experiences would still feel real from the inside. Joy would still feel like joy, love would still feel like love, and suffering would still matter. Meaning, connection, and ethical care would not disappear simply because the underlying layer of reality turned out to be different from what we once assumed. Again and again, we have encountered mystery. Each answer seems to open into deeper questions, and every layer of explanation reveals further depths that remain beyond our reach. Perhaps this is one of the most important lessons of all. Reality is mysterious. Consciousness is mysterious. And existence itself carries a depth that cannot be completely unfolded by the human mind. We live in a universe we do not fully understand, experiencing awareness we cannot fully explain, taking part in a story whose ultimate background remains hidden. And there is something quietly beautiful in that. It means we are part of something vast and subtle, something that exceeds our concepts and invites our wonder. Whether we are simulated or fundamental, whether consciousness is computational or something more, whether reality has many layers or only one, we are here in this moment, aware, breathing, sensing. That immediate experience is the most direct truth we have. And the simple fact of being alive and aware is extraordinary. You are a part of the universe that can look back at itself, that can ask questions about its own nature, that can feel curiosity about where it all comes from. Simulated or not, that is a remarkable situation to be in. As you gently return from this wide contemplation, you might carry some of these ideas with you, not as fixed beliefs, but as open possibilities that stretch the imagination and keep the sense of wonder alive. They can be thoughts you visit from time to time, quiet doorways that lead back into awe and reflection. The universe, whatever its ultimate nature, is filled with beauty. The patterns of physics have elegance. The structure of reality shows astonishing complexity, and consciousness allows experience to arise at all. These are things worth appreciating in their own right. Your own life, with its happiness and sorrow, its closeness and distance, its moments of clarity and uncertainty, holds meaning. That meaning does not depend on whether this world is simulated. It grows out of your lived experience, your relationships, your values, and the way you meet each moment. So as this part of the journey comes to rest, allow your awareness to settle back into the present. Notice your breathing. Sense the space around you. Feel the simple presence of being here. The great questions about reality can soften into the background, available whenever you wish to revisit them, but not demanding to be solved right now. They can remain like distant stars, expanding your sense of possibility without weighing on your mind. In the end, what matters most is not the final answer about the structure of the cosmos, but how we live, how gently we treat one another, and how openly we meet the mystery of existence. Whether in a simulation or in a fundamental universe, we are conscious beings capable of care, understanding, compassion, and growth. Let your mind grow quiet now. Let your thoughts slow. The questions are still there, but you do not have to chase them. The mystery remains, and you can rest peacefully within it, knowing you are part of something vast, strange, and deeply beautiful.